Okay, so we gradually start today's session. Today's speaker is Shuntaro Tsubouchi, who is a student of a graduate PhD candidate of University of Tokyo. He's going to face PhD defense in the next few months. Although he's a good graduate student, he already contributed a lot about regularity theory. He already published 3 papers. One is calculus variation, one of the one is archive rational mechanics analysis, and also recently mathematician Allen. And he's a very specialist. He solved a very important problem related to Bingham fluid. Related to fluid mechanics. Okay, so today he's going to talk about continuity of spatial derivative for perturbed one-Laplace equation. So, Mr. Tsubouchi, please.
Thank you for your kind introduction. I am Shuntaro Tsubouchi. I would like to express my deep gratitude to organizers, including Professor Howard and Professor Giga, for giving me a nice opportunity to talk about my recent works. Now let's start. My talk is concerned with C1 regularity results on weak solutions to this very singular elliptic equation in a multi-n-dimensional domain omega with Lipschitz boundary. The divergence operator delta 1 and delta p are respectively the one-Laplace and the p-Laplace operator. The left-hand side of this equation is often denoted by LBPU, where the fixed number b is positive and the fixed exponent p is greater than 1 and it is finite. The unknown real value function u is assumed to be in the first order Sobolev space W1P, and therefore we consider weak solutions in the sense of distribution. For a given external force term f, we assume that this belongs to a Rubik space LQ with the exponent q greater than n. Please note that this condition on Q is optimal when we consider gradient header regularity for example, Poisson equations. I like to emphasize that our methods in this talk still work even for vector value problems, so we may let U and F be cap R vector valued. This will be explained later when some generalizations are discussed. This elliptic equation, as well as elliptic system, is derived from the following Euler-Lagrange equation. Here, the corresponding energy F contains the sum of the total variation energy and the p-Dirichlet energy. This type of energy functional often appears when one considers fluid mechanics and material science. A typical example is Bingham fluids, including oil, toothpaste, and various fluids that contains both plasticity and viscosity. Plasticity and viscosity effects herein correspond to respectively one-Laplace and two-Laplace operators. This kind of property is often said to be viscoplastic. In this model, U denotes three-dimensional velocity of a Bingham fluid. When U is sufficiently small so that the convention effect can be abandoned, this U satisfies a second-order elliptic system of Stokes problem, where F becomes F is a slope minus a slope of a scalar valued pressure function. So anyway, it is important to consider vector valued problem. However, when we consider a unidirectional Bingham flow in a cylinder pipe, then this Stokes flow problem becomes our equation in a two-dimensional domain, and this F becomes constant. For the detail, please find a monograph by Dubart and J.L. Lyons. Another example is found in crystal surface growth under roughening temperatures, which was modeled by Spohn in 1993. There, the crystal surface energy is considered with P equals 3, and here, a scalar function U denotes the height of crystal, and F corresponds to a chemical potential. The resulting equation itself is a fourth-order parabolic problem. However, in the stationary case, this big problem becomes a second-order elliptic problem with P equals 3, and F is sufficiently smooth. On these mathematical formulations, please find Spohn's paper and Korn's monograph related to fourth-order problems. So for this equation, its gradient is expected to be at most Herder continuous. More precisely, for a given energy density E, its convex Fenshill dual E star satisfies the following identity. So in particular, the convex Fenshill dual becomes a weak solution to this equation where the external force term is minus n. So in particular, the convex dual Fenshill dual often gives optimal regularity. In our case, the convex dual function is in the class C1 alpha with alpha given by this. So therefore C1 alpha is best possible regularity. However, this C1 regularity conjecture has not been answered affirmatively. But in my talk, I'd like to say that at least C1 regularity, it is true. Now, I will state the main C1 regularity theorem in this slide. Before stating my results, I briefly mention P Laplace regularity. If we remove the one Laplacian and consider P Poisson or P Laplace problems, then it is well known that these weak solutions in the distribution sense are always continuously differentiable. Moreover, a gradient is always Herder continuous. In this sense, P Laplace operator keeps continuity of gradient. In this slide, I have listed a few fundamental works, and there are many excellent experts who established P Laplace regularity theory. Although Herder gradient continuity for P Laplace type problems has been well established, when P equals 1, it is no longer possible to obtain continuity of derivatives. In fact, even in the simplest one-dimensional case, any absolutely continuous scalar function like this one becomes one harmonic as long as it is non-decreasing. In particular, C1 regularity of weak solutions is no longer hopeful, even for one Laplace equations. This problem is substantially due because ellipticity of the one Laplace operator always degenerates in the direction of a gradient. This will be explained later by some explicit computations. So in this sense, one Laplace operator breaks continuity of a gradient. My recent result is when it comes to at least C1 regularity, for 1P Laplace or 1P Poisson type problems, P Laplacian will defeat one Laplacian. This result is valid even for vector-valued problems or system cases. Although however, we mainly talk about the scalar case for simplicity. When I was in the master course, I already answered this C1 regularity problem, partly in a special case where solution is both convex and scalar valued. That work was already published and is a joint work with Professor Giga. The methods therein are heavily based on convex analysis and a strong maximum principle. In particular, a gradient is regarded not only as a distribution, but also as a subgradient of a convex solution. This makes it rather elementary to prove continuous differentiability. My recent result removes this convexity assumption and also gives a similar result even for the system case. In this talk, I would like to briefly tell how to prove C1 regularity without these assumptions. So, the contents in my talk are as follows. In the first section 1, we would like to explain what is the main difficulty on our problem. It will also be demonstrated how and why C1 regularity can be reduced. The basic strategy itself can be found in recent researches on a certain very degenerate problem. In this section, I will also compare our very singular problem with a very degenerate one. Roughly speaking, we would like to prove a priori Herder estimates on a certain modulus truncated gradient. In the next section 2, I will give some sketches on showing a priori estimates. This section broadly consists of an approximation argument and a priori estimates based on de Giorgi's truncation and freezing coefficient arguments. Finally, in section 3, I would like to briefly talk about some generalizations and some future works in a few slides. So this is the end of section 0. Now we move on to the first section 1. To explain our main difficulty, we would like to introduce a real-valued convex function ES. So this is the energy density. Then it is easy to calculate the Hessian matrix nabla to ES by this one. And in particular, the eigenvalues and eigenspaces of this Hessian is easily given by this. All eigenvalues and all eigenspaces are given by this one, given by these. So please note that when S equals 1, this eigenvalue becomes 0. So in particular, this Hessian matrix nabla 2 E1 always takes 0 as an eigenvalue, even when the point Z0 is not the origin. So this fact means that even when the gradient does not vanish, the one-Laplace operator becomes degenerate elliptic in the direction of a gradient. Such property is substantially different from p-Laplace operators. Also, we should note that ellipticity of the one Laplacian in other directions never degenerates, and even worse, this ellipticity will become singular elliptic near a facet. A facet is a place where a gradient vanishes. So, in other words, the one Laplace operator contains both degenerate and singular ellipticity. Such anisotropic diffusivity of one Laplace operator will be, I think, very difficult to handle in existing regularity theory. Now we set the energy density E by BE1 plus EP. Then we can similarly compute the ellipticity, the Hessian of this E. And moreover, we can compute the ratio, which is often called ellipticity ratio. This is defined by the ratio of the largest and lowest eigenvalues of this Hessian. Then by seeing the previous calculation results, this ratio can be explicitly given by this. And please note that this negative power, this bz0 norm powered by 1 minus p appears, and this exponent 1 minus p is negative. So this is the main difficulty. In other words, this FTC ratio will blow up as this to 0 tends to 0, goes to the origin. The result implies that our problem will become no longer uniformly elliptic near a facet. Some of you might recall so-called PQ growth problem or non-standard growth problem. But this is substantially different, or problem is substantially different from PQ growth problem, since on PQ growth problems, non-uniform elliptic structures appear as a gradient blows up, not as a gradient vanishes. So in our problem, the exponent 1 minus p is negative, while on PQ growth problems, the corresponding exponent is positive. This is the main difference. Also, we should note that when b equals 0, this FTC ratio is everywhere bounded. So in particular, Helder continuity of a gradient is naturally expectable for p-Laplace type problems. Anyway, let's go back to our problem given by this one. Now we formally differentiate this equation by the spatial variable xj. Then we have the following equation star. The main problem in this equation is very simple. The coefficient matrix nabla2e nabla-u is no longer uniformly elliptic near a facet. So this fact prevents us from using basic standard tools from DeGeorge-Nash-Moser theory to prove Helder continuity of a gradient of a spatial derivative. In particular, it will be very hard to give quantitative growth estimate, gradient growth estimates across a facet. Also, another problem related to Sobolev regularity will appear. More precisely speaking, we formally deduce this equation, but this equation will no longer make sense in W-1, 2, because to verify this, we should prove W22 regularity of this term, of W22 regularity of U. However, this appears to be impossible. This appears impossible because standard difference quotient arguments will no longer work because our problem is no longer uniformly elliptic. This problem is substantially because the very singular operator is not uniformly elliptic. Therefore, we should relax this one by uniformly elliptic and also non-degenerate elliptic operators. So anyway, in previous slides, we have observed that our problem will appear near a facet. Still yet, there is a hope for C1 regularity. In fact, we should recall that ellipticity ratio can be controlled by this term, and if the norm of nabla-u exceeds some positive delta, then this ellipticity ratio becomes bounded, dominated by delta. In this sense, our problem can be said to be locally uniformly elliptic outside a facet. So with this observation in mind, we would like to introduce a modulus truncated gradient d delta nabla-u defined by this one. Please note that this vector field is clearly supported in a place where a gradient never vanishes, and therefore this equation becomes uniformly elliptic in the support of d delta nabla-u. So therefore, it is expectable that this vector field will be Helder continuous. However, we should emphasize that this header exponent alpha substantially depends on delta. And therefore, this here alpha regularity will blow up, will blow up as delta, the truncation parameter delta tends to 0. However, it is possible to deduce C1 regularity because the truncation mapping G delta approximates the identity mapping uniformly in Rn. So in particular, if we succeed in showing continuity of this modulus truncated gradient, then it is possible to deduce continuity of a non-truncated gradient. So this completes the proof of C1 regularity, as long as the continuity of this modulus truncated gradient is proved. This type of strategy itself can be found in very degenerate elliptic problems. And so I'd like to introduce some regularity results and some backgrounds on very degenerate elliptic problems. The main difference is very simple. The energy density is replaced by its convex spatial dual. This type of problem itself at least goes back to energy minimizing problem related to congested traffic dynamics, modeled by Carrillo, Jimenez, and Sant'Ambrosio. Please note that the same energy density is treated, but the detailed settings are different from ours. In particular, on this minimization problem, it is well known that this minimizer is explicitly uniquely given by the vector field nabla E star nabla V. Here this V satisfies this very degenerate elliptic equation. This is so-called duality formula, and that was proved by Brasco, Carrier, and Sant'Ambrosio. Anyway, it is natural to consider that higher regularity for minimizers. So higher regularity of this vector field is a good regularity problem in very degenerate problem. A well-known fact is that for each fixed truncation parameter, strictly truncated vector field G B plus delta nabla V, which is defined similarly to ours, is continuous. So in particular, the limit Z B nabla V and therefore optimal traffic flows are also continuous. This regularity theorem has been shown by 3 papers. The first work by Sant'Ambrosio and Vesely deals with the special case when the space dimension is 2. And the second by Colombo and Figari generalize the space dimension n and the convex density function E star for scalar problems. The third by Bogarin, Duzal, Jova, and Passarelli di Napoli was recently published and establishes vector-valued problems. Our proof of a priori held estimates is highly inspired by this third work. In particular, similar to this work, we would like to appeal to standard analysis, including De Giorgi's truncation and freezing coefficient methods. So I'd like to make some comparisons between very singular and degenerate problems. The right-hand side is a very degenerate problem, where the energy density is the convex dual of ours. When I happen to see these works on very degenerate problems, I came to think that these problems will be siblings, although their diffusion structures are totally different. In particular, I have expected that elliptic regularity can be deduced similarly to the very degenerate problems. So my recent work is a counterpart of that for very degenerate problem. I believe that this energy duality gives us more regularity expectations, not only for elliptic cases, but also for other cases, which will be mentioned in the end of my talk. This is the end of section 1. Now we move on to section 2. First of all, we give the definition of weak solutions to our problem in the distribution sense. The key point herein is that over a facet, the term nabla-u over the norm of nabla-u does not make sense in the classical sense because the norm function loses its differentiability at the origin. Therefore, we should treat the term the one-Laplace operator as a divergence of an L-infinity vector field Z satisfying this subgradient property. The subdifferential set of the norm function is given by this. Of course, there might be some possibility of generalizing the norm function, and in fact, at least I have succeeded in considering positively one homogeneous density functions. This will be explained later in the last section 3. So in particular, one Laplace operator can be generalized. So one Finsler Laplace operator can be discussed. So anyway, as mentioned in section 1, we should consider an approximation problem so that Sobolev regularity can be improved. In particular, the very singular elliptic operator should be relaxed by uniformly elliptic operator LBP epsilon. This is explicitly given by this. This approximation this relaxed operator naturally appears when we relax the energy density by this E epsilon. In particular, the one Laplace operator is relaxed by some sort of minimal surface operators. For this regularized operators, this equation will become uniformly elliptic because the corresponding ellipticity ratio of the Hessian becomes everywhere bounded. And therefore, standard methods including difference quotient methods and de Giorgi-Nashimoza theory will work. However, we should note that this ellipticity ratio can be measured by another modulus, which includes the approximation parameter epsilon. So anyway, we have already mentioned that it is important to consider approximation problems. So we would like to explicitly give this approximation problem. This is given by the equation E epsilon. Here the external force term F is also relaxed by F epsilon. For this F epsilon, we only require weak star convergence in LQ. So in particular, we may let F epsilon be sufficiently smooth. Under these settings, the following proposition holds. So this justifies that a weak solution of approximated problem will converge to the original equation in a suitable sense, in the sense of W1P, strongly in W1P. This is a very good result. So this result itself follows from strong monotonicity of P Laplace operator. Please note that with the one Laplace operator alone gives no quantitative estimates, no good estimates, because the one Laplace operator always degenerates in the direction of a gradient. So in other words, or or solutions can be relaxed by the weak solution of this Dirichlet boundary problem. Unique existence of this problem is easy to check by appealing to standard methods from calculus of variation, including direct methods. Therefore, our problem is reduced to a priori header estimates for approximating equation. So we would like to prove we would like to show header continuity estimates related to modulus truncated gradient. Before stating the key estimates, we would like to give two remarks. The first is that this approximated solution all admits local W22 and W infinity local regularity. Now, this is possible because the relaxed operator is no longer is uniformly elliptic. Moreover, this is non-degenerate, and therefore we can make use of standard difference quotient arguments. So this regularity is expectable, and in particular, this equation makes sense in W-1, 2. The second is that we should adopt another modulus that measures ellipticity ratio for this approximation problem. More precisely, this Hessian matrix, this type of eigenvalue estimates can be deduced, and therefore ellipticity ratio can be measured by V epsilon. So we should adopt another modulus that includes the approximation parameter. With this in mind, when showing a priori header estimates, we should introduce another modulus truncated gradient given by G2 delta epsilon. Anyway, it is possible to prove header continuity of this modulus truncated gradient, and header estimates does not depend on the approximation parameter epsilon, while this estimates may depend on delta. Oops. This regularity result enables us to apply Altair-Ascoli theorem to conclude that G2 delta nabla U is header continuous. Roughly speaking, or analysis differs when a gradient or a modulus V epsilon degenerates or not. This can be judged by measuring super-level sets. For non-degenerate case, we like to appeal to freezing quotient arguments or a comparison to harmonic functions to prove a Campanat decay estimate. Campanat decay estimates for some Campanat decay estimate. For otherwise, for degenerate case, we may face analysis over the facet, but we do avoid this analysis by appealing to de Jong truncation. So by appealing to this truncation, then this equation will become uniformly elliptic, whose uniform ellipticity may depend on delta. So this is a technical part that avoids non-uniform ellipticity or anisotropic diffusivity near facet. In any cases, we can conclude that this D2 delta epsilon nabla U epsilon does always satisfy this Campanat type growth estimates. And therefore, C alpha regularity can be deduced. So this completes the proof. I would like to emphasize that such division of cases based on measuring a size of super level sets itself, this strategy itself can be found in Dependent Friedman's fundamental work on p-harmonic regularity, p-Laplace regularity for parabolic problems. So this strategy itself is standard, but we should avoid analysis near a facet. So this is the end of section 2. Finally, I would like to talk about some generalizations of our problem and some future works. Generalization of a problem differs when it is scalar valued or vector valued. I'd like to discuss each case briefly. In the scalar case, we are able to generalize both one Laplacian and the p Laplacian. In particular, the total variation energy is extended to a positively one homogeneous energy functionals. Here, the positively one homogeneous means that E1 satisfies this identity, always satisfies this identity. Clearly, the norm function satisfies this one. So in particular, the one Laplace operator can be generalized to a Finsler one Laplace operator. And on this problem, approximation schemes should be replaced. And on this non-symmetric problem, we'd like to appeal to straightforward approximations based on convolution by Friedrichs modifiers. The results on scalar valued problems as being already submitted in a certain journal, and its preprint is found in arXiv. In the system case, however, the density E is required to be spherically symmetric. This is often called Rn-Beck structure. This is the Rn-Beck structure. It is well known that without such symmetry, everywhere regularity of weak solutions is in general impossible. For this reason, one Laplace operator should be the one Laplace operator cannot be generalized. So this symmetric assumption is used to deduce weak formulations on this V epsilon. So the corresponding approximation scheme is given by this, and this is very similar to our model cases. In both cases, the energy density is required to be at least C2 outside the origin. Also, EP has a P Laplace-like structure. So anyway, general 1P Laplace type problems can be shown. C1 regularity for general 1P Laplace problems can be shown. This is what I mentioned in this slide. Now, in a few slides, I'd like to mention some future works. I have raised a few in this slide. The first is gross estimates of a gradient across a facet, but less is known about this. The main difficulty is our problem becomes no longer uniformly elliptic, and therefore the standard isotropic analysis is no longer useful. So this is a very challenging problem. It is a very challenging problem. The second is alternative analysis methods for anisotropic problems, in particular for non-divergence problems. In particular, localization arguments can be found in various regularity results, including infinitive harmonic problems and C1 regularity for variational minimizers for some strictly convex energy functionals. Among them, it is surprising that Evans and Sabine established C1 alpha regularity for infinity harmonic equation for the two-dimensional case. Infinity Laplace problem is also one of the anisotropic problems. Compared with these works, analysis is rather based on standard variational analysis, which may not work for non-divergence problems. The third is continuity of a spatial gradient for parabolic problems. For p-harmonic closed, the continuity of a spatial gradient is well established when p exceeds 2n over n plus 2. For the external force term f, it is natural to let the exponent q be greater than n plus 2. Under these settings, is it possible to prove that a spatial gradient is always continuous? This is now in progress, and I would like to answer yes. However, in addition to these settings, another restriction on P and Q is technically required. More precisely, we should require that the sum of P inverse and Q inverse does not exceed 1. This assumption will be explained later in the next slide. For the parabolic problems, the function space and the test function space are given by these. In particular, the solution is in LP W1P, and its time derivative is in LP prime W minus 1P prime. And we are able to similarly define the weak solutions for the parabolic problems. Also, there are 3 remarks on these conditions. When P exceeds 2n over n plus 2, then we are able to use Gelfand triplet, these embeddings, and therefore we can use Lyon's Martinez lemma and Aubin-Lyon's lemma. Moreover, under this setting, existence theory for weak solutions for P-Poisson type problems is well established. For details, please find a book by J.L. Lyons and another one by Showalter. However, on this formulation, F is assumed to be in LP prime W minus 1P prime. So for this reason, LQ should be continuously embedded in LP prime W1 minus 1P prime. So to verify this, we should use this condition, another condition. So this condition will be required when showing convergence on approximation solutions. Anyway, under these settings, it is possible to deduce a continuity of a spatial gradient. In the last slide, I'd like to mention the duality connections. I encountered with regularity results for very degenerate problems. I found that it is possible to show elliptic regularity for very singular equation problems, similar to very degenerate one. I believe that these problems are siblings because of energy duality. And so therefore, these regularity results will be, I think, siblings. I'd like to conclude my talk by giving a simple question. can we find siblings on parabolic regularity and partial regularity related to continuity of a spatial gradient? For degenerate parabolic problems, a few regularity results have been established by Ambrosio, Gentile, and Passaretti Napoli, but continuity of a gradient remains open. Recently, I have partly shown continuity of a spatial gradient for very singular parabolic problems, and I believe that another parabolic regularity result, like a long-lost sibling, can be found even for this very degenerate elliptic problem. This is the end of my talk. Thank you for listening.
Thank you very much for your very nice talk. So are there any questions and comments?
If you have
Maybe
questions, please raise the hand.
Yes, please raise a hand. Maybe it's let me start my question. I think you assume omega is a Lipschitz domain. Where do you use this kind of assumption in your argument? Oh, your microphone is off, I think. I cannot hear.
Oh, sorry. Oh, sorry. Well, Lipschitz boundary condition is used when we apply the compact and compact embedding more precisely. In the proof of this proposition, we have to use the compact embedding LQ prime into W minus 1 P prime. So to verify this compact embedding, a compact embedding should be used. So this is the reason why.
Thank you very much. Are there any questions and comments? Okay, Daniel, please.
Okay, so I have several questions. So with the siblings and when you go at the beginning, you were mentioning some results from Sant'Ambrosio, I think. So so my question is, I did not really understand. So do they use the duality problem and they know the regularity of the duality problem in order to basically deduce the regularity on the primal problem? Or what was exactly the reason why you showed us the duality problem?
Sorry.
So can you go to the slide of where you mentioned
how duality problem relate to your problem?
Yes.
So do you did you use a duality problem in your study or just analogy? I don't know. Could you clarify? Do you use the duality result, or you just show as a similarity?
Yes. Well, the mouse cursor doesn't work well. But for very singular problem, anisotropic structure strictly appears at the facet, while for the very degenerate problem, anisotropic structure strictly appears in the very degenerate set, and so these siblings have non anisotropic structures between conical singular point, a conical singular point, or vanishing place. So well, corresponding to these these anisotropic structures, elliptic regularity these similar regularity, C0 regularity are shown. So well, both of them will be anisotropic, well, what to say?
No, no.
Well,
I think Daniel's question is if you have the regularity result for very degenerate problem, is it possible to get regularity result for very singular equation or not?
well, this is very formal, but I think that sorry, my mouse doesn't work. Where is it? No, mouse cursor doesn't appear. Well, sorry, maybe. Sorry, please wait.
Oh, yeah, it works.
Okay. Well, so I think I formally think that this C0 regularity and this C0 regularity are just similar, and so the energy duality corresponds to very similar regularity results. Well, what to say? This observation itself, my observation itself is very formal, but the energy duality corresponds to regularity duality. This is my formal observation.
Okay, no problem.
But the proof does not depend upon as a result, right?
Yes. The basic
not.
strategy itself very different because the energy density, the density structure is very different. So,
okay.
So we should
what you say is, yeah, what you would like to say is the result has a similarity, but
yes,
the proof is quite different.
yes, yes, that's right. Because the diffusion structure are totally different. So, regularity observations are very similar, but to give a rigorous proof, we should appeal to other computations, different computations.
Okay, maybe this point, maybe we'll discuss in the coffee break. Maybe
Yes,
this will be
yes, that's
very
right.
technical. Maybe.
Yeah.
Are there any questions, any comments?
Yeah, Professor Giga, there is Professor Bobkov. He wrote a question in the Q&A section.
Q&A, okay, just a second.
Should I read it or you can see it?
Okay, I'll read it.
Oh, yes.
Can anything be said about the regularity of solution of the one infinity Poisson problem when P tends to infinity?
To my knowledge, not well, one infinity Poisson problem will be, I think, very difficult because one Laplace operator has an anisotropic structure, so does infinity Laplace. I think there is no fundamental works. There are no fundamental works on one infinity Laplace problems. Both of them are anisotropic. So I think
a good question,
very difficult to control.
That's a good question. Even infinity Poisson problem itself is difficult.
Yes.
So, okay.
Yes.
So Professor Bobko is fine?
Yes, I think it is answered.
Okay. Are there any further questions? No questions?
I have one other question. If there's
Sure.
So what about, so you used, of course, as a toy problem or as a main problem, the one Laplace operator. But what would happen if you replace the absolute value by a sublinear function? So you have convex integrants. Assume that the convex integrand has maximal growth, almost sublinear growth. So then you can produce with calculus of variation variational method, you still can prove existence of solutions for the Poisson problem.
Yes, yes.
And even if you combine it with the P-Laplacian, so it would be so that means you would need basically another example would be if the B in E1 would be X dependent, for instance.
Oh yes. Well, as far as I have tried, E1 should be positively one homogeneous, but I believe that it is generalized. It is possible to generalize more superlinear functions. However, we have defined the weak formulations based on subgradient structures. So I think the main difficulty will be to verify the existence of such a subgradient vector field. So I have just succeeded in a case where the energy density is E1 is positively one homogeneous. But the proof itself will be rather elementary, but the generalization will be, I think, possible, but maybe difficult. Less easy to prove, I think. Less easy to generalize. As long as E1 is positively one homogeneous, this can be elementarily shown.
Okay, thank you.
Okay, I think it's a good time to stop. Thank you very much for your wonderful talk, and we would like to move to coffee room, right?